Hi, I'm Peyton Kilborn, and this is my Physics 2212 Lab 1, the charge tape experiment. The purpose of this lab was to use common laboratory materials, such as pieces of tape, to create and generate an electrical charge, and then from there, create and study an electric field, and then analytically solve the strength of that electric field. And this is all for better understanding of the key concepts of electric fields. Now we break down the key ideas. First one, first one that we needed to get this knowledge was that when the tape is levitating above the other piece of tape, it means that the electric force and the force of gravity are balanced, just in opposite directions. And then the second key one is the opposite charges will attract and like charges will repel. This is how we had the two pieces of tape repelling each other, causing one to levitate, which was the work product of the experiment. And the relevant equations are the static force equilibrium equations, where we can see that the sum of the forces are zero, allowing us to solve for electric force. Coulomb's law, the equation we actually use to solve for electric force, and universal gravitation, simplified into F equals mg, showing that's the universal gravitation is the down force on the tape. Coulomb's law is the force propelling it upward, and static equilibrium just says they're equal. This is the image we have of our piece of tape levitating due to both them being positive charges repelling. This is my GlowScript code. As at this top, you can see universal constants. Below that are initial conditions, such as the tape being 3 centimeters higher than the other piece of tape, the mass of the tape, the position, and then below that, you can see that is my calculations to get to the Q coulombs Q charge for the electric field. And then even more below that, we see it generating my actual digital digital force balance, which we can see right here. The ball represents a piece of tape, and we can see the force of the gravity is the green arrow pulling it downward. The electric force is the orange arrow propelling it upward. The force of them will both be the same at the 9.8 times 10 to the negative fourth newtons, and the required charge magnitude I found to be 9.905 times 10 to the negative ninth coulombs. Every lab will have some sort of error. So in this lab, we originally assumed both tapes were assumed to be point charges, when in reality the charge would be spread out across the whole surface area. This was done to keep it in one dimension, because as you can see here, the two tapes are not aligned perfectly. We would have to consider forces in x, y, and z instead of now the way our assumption made it just consider forces in y. The net force in the y will always be the same no matter what a system assumptions we make like that, because those two pieces of tape being our system, they don't get impacted by the coordinates we choose. It would be only the surroundings, which is everything but the piece of tape, that would. And then we assumed that the two tapes would have the exact same charge since they're prepared the same way, but the using force to rip them apart is not the most accurate, so there could be some differences in charge. And we discounted variation in height from the tape and assumed that 3 centimeters, which was the average, could be assumed to be true throughout. Moving on to the what does it mean portion. What would happen if I flip the charges? So instead of both being positive, they'd both be negative. Nothing would change, as we only care about difference in charge rather than the charge magnitude itself. Why is it important to handle the tape as little as possible? So that it's a charged object, you don't want to ground it, and you'll connect a circuit with the earth, yourself, and the tape, grounding it, blocking off the charge. So we want to not do that so we can keep the tape functional as much as possible and reduce the need to recharge the tape.